All right, question number 2. I think we did similar questions. Maybe we did even do that questions, but I'll do it anyway. So you have a Gaussian vector center, you have a covariance matrix. All right, first question, is this vector non-degenerate? And the answer is no, non-degenerate. So the answer to that is obviously yes, it's non-degenerate. You just calculate the determinant of C. It's not equal to 0. B, argue that x3 is independent of x2 and x1. So this is because x1, x2, x3 are jointly Gaussian. And so you have the Gaussian miracle. We use the miracle. Only have to compute the covariance. So I have to compute the covariance of x3 with x1. But by the covariance matrix, that's 0. Just look at the 1, 3 entry. And same thing with x1, x2. Great. So AB is done. Okay, 4 points. I'm going to pass this class. Now question C, I want to compute the conditional expectation of x2 given x1, and then I have to write x2 as a linear combination of x1 and a variable independent of x1. Okay. So to do this, what do I do? Well, I know that the expectation of x2 given x1 is the projection, and in the case of projection, all the random variables I can construct from x1, and in the case, this is because it's Gaussian, it's very special. We saw the formula, so this is exactly the projection, exactly on multiple of x1. So it's the covariance of x2, x1, divided by e of x1 squared, x1. So we saw that in class. So now I have the covariance matrix on all the covariances. So x2, x1 has covariance 2, and the variance of x1 is 2. So I get 2 over 2, x1. So the conditional expectation is simply x1. Very simple. So I can write actually x2 always as x2 minus the conditional expectation plus the conditional expectation. Okay, that's nothing. I just added and subtracted the same thing. Now what is great is that these two random variables are orthogonal. And that implies, so you can just compute the covariance, that implies, because they're Gaussian, again, covariance 0 means independent, that they're independent. So this decomposition is the orthogonal decomposition is actually independent decomposition for Gaussian. Right? And I know what is the conditional expectation is just x1, so I can write this x2 minus x1 plus x1. Again, this seems like obvious. But remember that what is not obvious is that these two are independent, so that's the great thing. All right. So that's question number 2. Question number 3 now, I want to compute the moment generating function of x2 given x1. And that will give me, since the moment generating function determines the distribution, that's going to be give me the distribution of x2 given x1, the conditional distribution. So let's do that. And now, my questions always depend on the previous one, not always, but often. So now I can write x2 as x2 minus x1 plus x1, ax1 given x1 by the previous question. And now, this is the great thing about conditional expectation. This variable e of ax2 minus x1, it's independent of x1. That's what we proved before, independent of all the random variables I can construct for x1. And this guy, I can take it out. So here I use the property of the conditional expectation. And I can write this as e of ax1 times, since it's independent, my best guess is just the expectation, ax1 times e expectation of ax2 minus x1. All right? Now, what's this? The first term is easy. The other term, x2 minus x1, is this random variable right here. It's a Gaussian, of course. It's the difference of two Gaussians are jointly Gaussian, so it's a Gaussian. So the mean is 0, because everything has mean 0 here. Now I just need the variance, but the variance of x2, I can check here, is 4. And the variance of x1 is 2. So the variance of x2 minus x1 is 2. So I get, so this guy has variance 2. Okay? And therefore I get e of a times the variance 4 divided by 2. So I get that this is e ax1 times e of 2a. All right? So what's the distribution of this? The distribution of this this is a square. Okay, so ax1, so let me erase that. This is ax1 plus 2a squared. Okay, so this has the form actually of a MGF of a Gaussian with mean x1, so a normal would mean x1, and variance 4. Okay, so this is kind of obvious already from here. Okay, so this is the mean. Every linear, I can always take it out, linear in the parameter. And what's left is this variable x2 minus x1, which is variance 2. I'm sorry. Okay, so this is variance 2. So I should get a squared variance 2, so it's 2 over 2, and the 2 cancels. I'm doing this live, so obviously mistake happens. Alright. So, plus a squared. And then, it's normal to do mistake. But it's not normal to stick to it. Okay, and the variance of that is 2. Alright? So that's it for D. And now I'll do E right here. So now I want the ID decomposition, but we did a lot of work, so now it's not a big deal. Okay, so always the ID decomposition, I start with x1. I have to normalize it, so I have variance 1, so it's square root of 2. Now you have Z2. Z2, so I know a random variable that is independent of x1. I found it in C, and that's just x2 minus x1. So this is a Gram-Schmidt. If you want x2 minus the part that is in x1, so it's minus x2 minus x1. If I want to normalize it, I divide by square root of the variance, so it's again square root of 2. And Z3, well, Z3 is just x3, but look at x3. We know that x3 is independent of x2 minus x1, and x3 actually has variance 1, so x3 is easy. Z3 is just equal to x3. Alright, so that solves it.